Hello everybody, thank you for joining us today. My name is Minim and today we're going to be looking at how motors work and how speakers work. So I've already said it, but those two are our only learning objectives, to understand how a motor works and to understand how a speaker works. So I hope you're ready, let's get right into it. Okay, so now let's first have a look at how a motor works. Now this diagram does look a bit complicated when you look at it straight away, but as always we're going to break it down a bit by bit till we understand it all. Okay, so I have here my battery. And that's connected to two brushes, right? Which is connected to something called a split ring commutator. Now, I'm going to ignore all of this for now, and I'm going to come back to it later, because you have to understand what's happening here first before you can understand what's happening on this side, right? But first, let's label the terminals in the battery. The long side is always the positive, so let's do that, and the short side is negative. And so again, we see that the direction of current flowing in the loop of wire here is, or rather coil now, is always positive and negative, and we can see that by the little arrows that are present. I'm not sure if you can see that, but if you can't, I'm going to add them in right now. Okay, you can see the arrows pointing the direction of the current. Now we also see that our current carrying conductor, our wire, or rather coil, is in between two magnets. Now these magnets also have a uniform magnetic field acting across them like this, right? And again, the direction of the arrows is always from north to south. Now, we just learned about something called Fleming's left-hand rule. Fleming's left-hand rule tells us the force exerted on a current, on a current carrying conductor is equal to the magnetic field strength multiplied by its current carrying in the wire and multiplied by the length of wire present inside the magnetic field. Okay, so that would be this length, actually let's do it in green so we don't get confused. That would be this length of wire here that's actually inside the magnetic field itself. Okay, now how do we work out the direction of the force? Well, we use Fleming's left-hand rule. I can see that my magnetic field, which is first finger, is going from left to right, so I do that. And now I know my current on the on the right hand side, so here, is going this way. Okay, so the current is going away from me, so the force is acting downwards, and that is represented here by this arrow here, that the force is going downwards. But now, if I have a look at the other half of the loop, the current is coming towards me. Okay, so if the current is coming towards me now, the force is acting upwards on that side, and that's represented here. So what I'm really getting is two opposing forces on the same wire. Right, so this is my axis of rotation here, right? So that's where it actually rotates. I have one force acting this way, and I have another force acting this way. Now, the overall force causes the coil to rotate, which is exactly what we want in a motor. We want the middle coil to actually rotate. And so this is why Fleming's left-hand rule and the motor effect are often mentioned in the exact same sentence, because Fleming's left-hand rule is how we can explain the motor effect, which is the effect of a rotating coil when a current carrying coil, or rather it's usually conductor, but we're talking about coils here, so it's good to use coil, is placed in a magnetic field. Okay, so we can see when we place this coil in a magnetic field and we run current through it, it starts rotating because there are forces acting upon each half of the wire. Now, as soon as the wire does one half turn, these forces flip, right? Because the direction of the currents flowing in the wires also flips, right? Because as soon as we've rotated our coil, now sort of the currents flowing in the opposite direction. That means that the coil will just rotate back to exactly where it started. Okay, that's a little bit difficult to get your head around, but as soon as you start doing the experiments in your class, I'm sure that you understand this, right? So how can we prevent the current from flipping every half turn? Well, we use something called a split ring commutator. So let's write that down here. So this keeps current flowing in same direction or rather it doesn't stop it flipping, because we can see that our split ring commutator has, well, a split in it. That means that one half of the loop is constantly connected to one terminal and the other half of the loop is constantly connected to the other terminal. So this means that that the direction of the current flow is in exactly the same direction, because the current actually never stops touching. Sorry, the current actually never starts touching the other terminal, right? It's a little bit difficult to work your head around, but as soon as you start doing practicality, which I can't really do for you right now, this all starts to really make sense. But if you're confused about anything else, please go back through the video and work through it slowly to understand how a motor works. And if you do, okay, so now let's have a look at how a speaker works. Well, the speaker but also works on a wire coil here, right? So that's our coil right there. I don't even have to label it because it's already labeled per habit. And then I also have a permanent magnet. Now you might be thinking, oh, this looks a lot like an electromagnet. Well, that's because it has exactly the same structure as an electromagnet, but the wire coil is not fixed. Okay, in an electromagnet, the wire coil is usually fixed around the permanent magnet, either with like glue or tape or whatever. But here, the wire coil was not fixed at all. Okay, it's just resting around the permanent magnet, and connected to the wire coil was our cone here. The cone is actually what does all of the real vibrating, right? So here I have my electrical signal coming in here, and this is AC, alternating current. This means that the electrons inside the wire are alternating at X frequency, right? So now that they're alternating at X frequency, this is kind of like the current is being switched on and off X times a second. So let's just say 100 times a second. Current is switched on and off 100 hertz. So that's 100 times a second. Now, what does this actually mean? Well, we know that if we have a current carrying conductor in a magnetic field here, which there is definitely a magnetic field produced around the permanent magnet itself, we get some type of motion. Now, we know that with Fleming's left-hand rule, right, that all of these forces act at 90 degrees to each other, and we can definitely see that. We can see that our magnet produces an electric field something like that, and our wire also has electric fields around it. So, our coil also has electric fields around it like that. So now, with all of this interaction between electric field, it's a bit too difficult to draw on here. Scientists have worked out a way to orient the coil and the magnet in such a way that the movement is always up or down. Okay, so now we know that the current is switched on and off. So when the current is switched on, we get a movement up, and when the current is switched off, we just fall back to our rest position, which is down. So if our current switches on and off at, say, 250 hertz, which might correspond to, I don't know, the frequency of my voice, that would mean that the cone vibrates at 200, what did I say, 250, right? 250 hertz, right? Say 250 hertz. So the current vibrates at 250 hertz, which means that it produces longitudinal sound waves, hence here, right? Because remember, the cone is actually hitting air particles every time it vibrates, right? Produces longitudinal sound waves, always kind of going there, at 250 hertz. That means that our eardrums also vibrate at 250 hertz, and so our brain turns that into a signal, and say that signal corresponds to my voice, or say the electrical signal is now 5000 hertz. Now 5000 hertz could be picked up as our brain as your favorite song. In reality, the electrical signal frequency is changing literally thousands of times every second, right? Which is why the sound waves all come out at different frequencies, and we hear different frequencies, etc. It ends up becoming slightly more complicated later on. But all you really need to know is that a speaker really works by the motor effect. An alternating current is passed through a coil, and that wire coil is placed around a permanent magnet. Okay, so our coil is also connected to a cone. Now, every time the frequency of the current, every time the current vibrates, right, through the actual coil itself, the current sort of switches on. And when this current is switched on through the coil experiences a force upwards, and so it vibrates. And now that really explains how a speaker works.